lab number 2. This has lots of content in it, so please be careful and feel free to re-watch the video at a later date. Okay, what we're looking at is our measurements and uncertainty lab. We've got a lot of different goals coming out of this lab. We need to safely use different lab equipment. We've got balances, thermometers, rulers, graduated cylinders, so lots of different things coming at you. We need to accurately report measurements from different lab equipment. Okay, this is also known as looking at the uncertainty of the instrument and its meaning. And then last but not least, we'll also be interpreting significant figures or significant digits. Okay, so again, lots of content. I'll try and go through it as quickly as I can, keep it under 15 minutes. First off, measurements and uncertainty. Okay, one of the big things that's different about a science class in comparison to pretty much any other class is that we have measurements. And with a measurement, we have both a number and a unit. So this means anytime you write down a number, you better write down the unit because the number is meaningless without it. Okay, so then the question becomes, well, what number should I write down? Okay, well, sometimes that's obvious, sometimes it's not. If we're looking at a ruler, we have to make sure that we're using the ruler appropriately. Okay, so if we're going to make a measurement, we're going to write down all of the obvious digits, everything that guaranteed it absolutely is that. And then we will add one more guess digit. Okay, one more guess decimal place. No more, no less, must be there. Okay, so let's take a look at distance or length. Okay, well, we have a little silver rod here lined up conveniently over ruler A. What is the length of that silver rod? So hopefully you came back from that question, and if I did it right, tricked you, because I don't think I actually had the answer there. So you probably guessed one of the other ones and thought you were right and found out you were wrong. Well, that's me, just being a jerk. Okay, so let's write down our obvious digits. Well, obviously, it's not 3 and it's not 5. So it's obviously 4 something. Okay, well, according to our rules, I can only add one more guess decimal place. Most students will say something like 4.25. Okay, and if we're going to be extra fancy, centimeters. The issue with this is that we have the obvious digit plus one guess. What is this 5? That 5 is a guess on top of a guess. So really what you're saying is you have no clue what that number is. That could be 6, that could be 7, that could be 42. We don't know. Okay? We can't write that number down because that now implies more information than our measuring device provided. Okay? That's why that is wrong. Okay? We can only provide one extra decimal place. That's it. Okay, so let's try a new one. Let's see what you can do with this. Okay, so now we're looking at ruler B, and I provided a little zoom in on the far right, just in case you needed that extra little view. Okay, hopefully, now that you're back with our video, you actually got a good answer here, and we should note that it is 4 point. And if we go through and look at our markings, we had a 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we moved up. Okay, we're absolutely higher than the 2, so 4.2. Okay, we're definitely lower than the 3, so the 2 is not a guess. And now I'm somewhere between the 2 and the 3. I'm not exactly at 2, and I'm not exactly at 3, so I need to come up with a guess. Well, I'm going to guess 4.26. Okay, and I'd be wrong. Oh my gosh, we just went through all this. Why am I wrong? Remember I said the unit? We need to include that unit. Okay, and now we've got our correct measurement. Okay, well, when do I have to do this tedious, nasty procedure? Every single time you make a measurement. That's it. Every time you do it. Okay, if you don't do it, you lose points. Okay, or you could result in kind of catastrophic mismeasurements and result in space shuttles exploding, because, believe it or not, that is possibly one of the culprits. Okay, so we have to be very, very careful in how we approach these. Okay? So what happens? Oh, actually, sorry. We had a little note there at the bottom. Uncertainty should always be reported with the measurement. Okay, which brings in the next point. how do we know the uncertainty of this? Because really that should say 4.26 plus or minus probably something on the order of 0.03 centimeters. This is our uncertainty. Okay, it's what's inherently wrong in the device. Okay, you probably didn't say 4.26. You probably wrote 4.25. Okay, well, we didn't get the exact same value. Well, that's because there's uncertainty. We're guessing at that decimal. How accurate is our guess? Most devices, if they are designed to be used in science fields, tell you that uncertainty. If not, guess it is that last decimal, and then you can kind of make up a number. I said 3 because I thought 1 was going to be too small. Okay. Really, the way we determine that exactly is we take this ruler, we throw it out to thousands of people, and we ask them to measure a rod. Then we look at all of their answers and see how far their answers were off from each other. Now we have the uncertainty. Do you really want to do that? Yeah, I didn't think so. Most cases outside of this specific lab, you will just see the number or the measurement written with the units. You won't see the uncertainty included. It should be there, but we don't do it. How about when we take a mass? Okay, well, these balances are pretty cool because they tell us the mass. Okay, so we need to write all the digits the equipment provides. Okay, but don't provide more digits. So if we were to look at these individual balances and write into our notebook what the mass was. Okay, so let's take a second and answer that quiz. Hopefully, what you're writing in your notebook is 16.43 grams. Good job. That one was straightforward. And on the other one, you were writing 100. Okay. Well, no, that was wrong. Okay, I'm sorry. I didn't want to draw all the zeros. You would write 1. No? Why not just 1? Well, because the instrument told me that I have those zeros. Why is 100 wrong? Because the instrument told me I had 3 more zeros. If the instrument tells you there's a 0, that's a measurement. It's telling you that value. If you decide to ignore it, instead by just saying 100, that is the exact same as me saying I will give you $100, but then only give you 1 because those zeros really didn't mean anything. Okay? So we need to include every single digit. Okay? Every single one. If it gives it to you, it's supposed to be given to you. Okay? Methods of weighing, this bears kind of repeating. Hopefully your instructor will go through and explain this as well. Okay? Direct mass of an object using the tare function to zero the secondary container. So we can put the weigh paper on the balance, then we can take the weigh paper off the balance, put our crystals into the weigh paper, and then put it on the balance. Okay? We can zero out the weigh paper to tare it so that it now ignores the weight of the weigh paper and will only measure what's being added to it. Okay? We could also do an indirect calculation by obtaining the weight of the secondary container first. So we put it on, we weigh it, and then we add our substance to the paper, and then we weigh it again, and then the difference between those is now the weight of the substance. Okay, so when you look at your lab manual and it's asking you these weird kind of calculations, this is what it's talking about. There's a direct mass and then an indirect mass. You should be getting roughly the same answer both times. The extra feature of the direct mass is it's a little bit easier than having to do calculations. I mean, calculators, God, whoever wants to use those. Okay, thermometers. Remember, we need to report all the digits the equipment provides. Okay, this gets trickier. What are the digits that the equipment provides? Okay, so we've got the zoom in to help you identify that, see what you can come up with. And what you will hopefully be writing into the notebook, and I've actually myself got to kind of draw this out, is we're looking at 23 degrees Celsius. But actually my line didn't go exactly through the black marking. It actually went somewhere in between, which means 23 is actually wrong. It's 23.2 degrees Celsius. Do I need to specify that extra 2? Yes. Yes, you do. So do it. Don't question it. Do it. Okay? That's why the markings are there. Take advantage of them. Okay? And it can be helpful to have a couple different people look at it. I've zoomed it in even closer here to help make it a little bit more obvious. You'll notice also that I drew my line from the kind of lower part because we're trying to show three-dimensional characteristics. It's just slightly above the 23 line. Okay? So we do need to take that into consideration. Okay? What about the units? Should we be using Celsius, Fahrenheit, or Kelvin? It's a good question. Okay? Depending on what use or where you're located even in the world, you may be using different things. Celsius seems to be the standard under most cases, okay, for most of the world. If you want to get all weird, we can move to Fahrenheit, and that really only works for US weather. Okay? And then Kelvin is kind of mixed with Celsius as the standard for science. And science is awesome, so of course that's listed in capitals. So again, depending on where we are, we might want to list different things. Well, how do we know which one we have? Because most thermometers will actually only tell us Celsius or Fahrenheit, but not Kelvin. And if they only tell us Fahrenheit, they won't tell us Celsius. So that means we need to be able to convert. Okay? So here are two conversions. We've got the degrees Celsius. So what I would do is plug in whatever number for my degrees Celsius here. Whoop, come on. Here. Multiply by 9. Divide by 5. And then add 32. Because that makes sense. This gets me my Fahrenheit value. To get to my kelvins, the kelvins come only from the degrees Celsius. All I have to do is add 273. The 0.15 just happens to be Mike showing off his knowledge on the extra sig figs that he remembers. Those are not a requirement, particularly for 130. Okay. So with that, we can move on to our liquids. Okay. We've got our liquid here. We do have an extra issue because some liquids will sag, and that gets us a negative meniscus, and some liquids bulge, getting us a positive meniscus, okay, like mercury. We will always read from the bottom of the sag, be it the top or the bottom of our sag or the top of the bulge. Okay, so if we take a look at our liquid over here, what would we write in our notebook? I'll again give you a second to come up with an answer. Oh, that's awesome that we've got markings there. So it is 1 tick mark. Not quite 1 tick mark above that. Since we didn't have lines, let's just say 10, 20. Can I do that? Yeah. 30, 40, 50. Okay, if you came up with a slightly different number, that's okay. And I would say 50.9. Okay. Yes, we have to report that extra thing. We're saying milliliters here. Okay. Is it tedious? Yes, but it's necessary. Okay. It is a requirement of using the device. Okay. Now to the fun part. We've now been able to report all these significant digits. What do we do with them? Okay, well, we have to be able to interpret them and decide what makes them significant. Inside the lab, we know they're significant because our device told us the number. Okay? If we're not told the number, or we don't have a device to tell us the number, how do we know what's significant or not? So we've got a sequence of 5 numbers here. Okay, and you're going to have a little quiz question pop up here. We want to know how many significant digits are in each. So let's take a look. 1, 2, 3, 2, 1. Okay, nice and symmetrical. How do we know that? Okay, well, you probably saw that each of those numbers had at least one significant digit, and it was probably the 1, the 3, the 2, or the 1. Okay, so we're really having a hard time understanding the 0. So we need to be a little bit more specific with our 0. Okay, 1 to 9 are always significant. Is the 0 significant? Brings in a new set of rules. Okay, those rules all come back to the decimal point. Is it there, and where is it relative to the zeros? Okay? So, the rest of our rules. If there is no decimal point, then the zero, to be significant, must be controlled by numbers to the left and right at any place to be significant. Okay? So no decimal point. If we go through and take a look at these with no decimal points, that's our first two. So for the 0 to be significant, I must look to its left. Do I have a significant digit? Yeah. I must look to the right. Do I have a significant digit? Yeah. That means the 0 is significant, and I have 3 sig figs. Okay. What about the next one? 1, 2, oh, there's another 0. I look to the left, what do I see? Well, a significant digit. I look to the right, what do I see? There's nothing there. Well, if there's nothing there, that's not a significant digit. If that's not a significant digit, then the 0 is not a significant digit, and I have 2 significant digits, or sig figs. Okay? That's how the rule applies. If there is a decimal point, then the 0 needs to be immediately preceded by a significant digit to be significant. So I have to have a sig fig in front. The rest of these are all examples falling under rule number 3. So if I take a look at the subtle change on moving from 120 to 120 decimal point, with that decimal point, I just have to look to the left. Is that a significant digit? Is 2 a significant digit? Well, yes. That makes the 0 significant. I get 3 sig figs. Okay. How about the next one? Take my first 0, I look to the left. Is that a significant digit? Yes, which then means the 0 is significant. I move to my next 0 and I look to the left. What do I see? Well, a significant digit. That means it's a significant digit. And I would have a grand total of 4 sig figs. Okay. With that, you can do the last column of 4 different answers, and we'll see some of those pop up in a little quiz. Last thing we want to get to with our, or almost last thing, scientific notation. How many significant figures in the following number? Well, hopefully if you've applied the rules correctly from before, you come up with 2. Okay. The rest of those zeros are not significant because I don't have a decimal point and I don't have a significant digit to the far right. Okay, so the zeros are now not significant. But what happens if I took this measurement and I was precise to the thousands place? Okay, so the thousands place, I'm saying that that 1 is for sure accurate, the 2 is, the 0 is, and that 0 is accurate. My device tells me I'm accurate to that place. Well, that says my answer should have 4 sig figs. But if I write the number 1,200,000, I don't know that those zeros are significant. What if I'd said to the tens place? Okay, that's 2 more zeros need to be significant. How can I report that number with the significance of those measured values without losing meaning? Okay, a common student assumption, well, let's just delete those zeros. Well, now it's significant. So my number that was 1,200,000 is now 1,200. That's your paycheck. That's a pretty significant difference. So we don't want to lose the zeros because the zeros are placeholders telling us where to put the significant digits. Okay, so we need the zeros there. So how can I report this number? This is where scientific notation comes in. In step 1, we'll place a decimal after the first significant digit. Okay, so in this case, our first significant digit for the thousands was 1. And then I'll place my decimal point. I'll then follow it by the remaining significant digits. So 2, 0, and 0, that gets me to my thousands place. Okay. Well, now I took 1 million, it's become 1.2. Ooh, that's a pretty significant issue. Okay, but step 2. Indicate how many places I move the decimal. Okay, and I forgot my notation here. We'll need a times 10 to the n. Okay, so I'm going to indicate how far I move the decimal by using the n. I'm going to change that n to a number. If the new decimal is to the left of the old, then I want a positive n. Okay, so I'm not going to like that. So we're just going to switch that already. Okay, is this number really big or really small? If it is big, then my n needs to be positive. How far did I move the decimal? Well, I went from 1, 2, 3, 4, 5, 6. 6 locations. Okay? That's how it works. What if it was a really small number? And I know I don't have that example. If it was a small number, then I'll make it a negative n instead of a positive, and everything works out. Okay? What if I wanted it to the tens place? Okay, well, how did that work? Actually, let's make that a question. You can answer that now as a question, now that I've erased all the answers. What would your answer be written as and accurate to the tens place? And with that, move on to the next big fun one, measurement versus exact. A distance, mass, volume, and time are only as accurate as the instrument measuring them. But do we have measurements that do not require an instrument? How many quarters are shown in the image? Well, if we count that out right, you should come up with 7 quarters. Well, how many significant digits are in that measurement? Okay, well, if I say 7 quarters, that's only 1, right? Okay, so what about 6.9 or 7.1? Okay, are there 7.1? No, there aren't 6.9 either. So maybe you're saying 7.0. Well, 7.01? Okay, no, there's a whole bunch of zeros after this. Okay, and that's exactly the point. There are now so many zeros that this value is exactly correct. And if it is exactly correct, it has an infinite amount of sig figs, okay, or significant digits. This is a challenging issue, and it largely comes up when we're counting usually small numbers. You'll also see it show up in conversion factors. Okay? How many inches are in a foot? Well, there's 12 inches equal to 1 foot. How many sig figs in 12 inches in this case? Well, it's infinite. There are exactly 12 inches in 1 foot. Exactly. And because of that, those values, or those numbers, have infinite sig figs. They aren't a measurement, they're a definition. Okay? And then lastly, what if we use these numbers? Okay? So if we did a multiplication, division, addition, subtraction, all that kind of fun stuff. Well, if it's addition, subtraction, our answer is only as precise as the least precise measurement. So if I'm going to add those two numbers up, I would get that out of my calculator, but I can't report that whole thing as my answer because I know nothing about that number. It could be a 0 or 9. Okay? Both are possibilities. That means I know nothing about this position. Okay? So I can't include that in my measurement. The results would have to be 1.33 grams. We do run into one extra caveat here, which I forgot about on this slide. Where is that 5? Is that closer to becoming 1.34, or is it closer to becoming 1.33? 5 is right in the middle. We have a rounding rule. Our rounding rule is that if that first non-significant digit is 5 or larger, then we add 1. So the reported value for my addition becomes 1.34 grams. Annoying? Yes. Do you have to do it? Absolutely more so. The next trick one that becomes irritating is multiplication division. The result is only as precise as the measurement with the fewest sig figs. This one's particularly irritating because everybody remembers the multiplication division one and nobody remembers the addition subtraction. You have to keep these two rules separate. They do mean different things. If we go through and multiply out, what do we end up with? Okay, well, we have 2 sig figs here. We have 3 sig figs here. That means our answer can be reported only to 2 sig figs. Our answer becomes 36. the first insignificant digit, larger than 5, I will add 1. My official answer is 37 units squared. Tricky? Bothersome? Yes. Okay, and it will take some time to get used to and have practice with. That's kind of why the lab is there, and we will see it in lecture if you have Mike a little bit later this semester. Okay, and with that, I believe we are done. Yes. Sorry that took longer than 15 minutes.